In the last class, we started discussing about noise, and here's a quick summary of what we learned in the last class. So, every resistor in thermal equilibrium with its surroundings at an absolute temperature T is associated a noise voltage source in series with it, and the noise voltage spectral density corresponding to this noise source is 4 kTr volt square per hertz. And as we discussed the last time around, the spectral density is independent of frequency. In other words, this is often what is called white noise, and the reason is simply the following. I mean, optically, if you have all colors, the resulting color is actually appears white to us, right. So, and colors in optics are basically because of the light of different frequencies. So, in a similar vein, if you have noise corresponding to all frequencies in equal strength, you know, it's called white. Obviously, if the noise spectral density is not uniform with frequency, then it stands to reason that this is called colored noise. Okay. So, then we saw that if you have a noise source with a noise spectral density given by SV of f, and it is processed by a transfer function h of f, the output noise spectral density is simply the input noise spectral density multiplied by the squared magnitude of the transfer function, all right. And the total noise is simply the integral of the noise spectral density and the output, which happens to be is that clear, people? Right? And we did our first calculation of this noise spectral density, assuming we have a first order RC network. Let us assume that we have this is an input, and the an RC network. The output consists of V in filtered by the first order RC transfer function. It also consists of noise whose spectral SVO of f is nothing but 4 kTr by 1 plus 4 pi square f square r square c square, and the mean square value of the noise, as we calculated the last time, was what was it? Kt over c, right, where k is Boltzmann's constant. And we also saw the intuition behind this apparently surprising result. Even though the noise source itself depends on the resistance, the total integrated noise apparently is independent of the resistance, and we reconciled that by recognizing that while it is true that the noise spectral density increases with resistance, the bandwidth of the transfer function from the noise source to the output also experiences a change in the opposite direction, and in this case it just so happens that the two of them simply cancel, right. So, the total the mean square noise is Kt over c. Now, what are the apart from just being a mere curiosity, it turns out that this result has quite some importance in practice, and here is an example where it plays a role. As we were mentioning, as we were talking about in the early part of the semester, we like to process signals digitally, which basically means that you take a signal, you sample it and you quantize it so that you have a digital representation of the input. And one way of doing this is to basically sample the input that you want to digitize, and then once you sampled it, you kind of look at that sample and then quantize it, right. So, quantization obviously takes some time. So, you need some place to store that input sampled value, and storage of something can only be done on elements that have memory, right. And so, it is either an inductor or a capacitor, right. And for reasons of size, it is often a capacitance, right. And so, for example, here is the most simple minded example one can think of. So, this is a switch, right, which is periodically operated. Let us call this signal phi of t. So, for instance, this is an example phi of t, this is the sampling period Ts. When the switch, when phi of t is high, the switch is closed. When phi of t is low, the switch is open, and therefore, when the switch is closed, what happens to the voltage across the capacitor? Well, when phi is high, the capacitor directly comes across the voltage source, and therefore, it tracks the input voltage, right. When the switch is open, well, whatever charge is there on the capacitor is trapped, and therefore, what comment can we make about the sampling instant? At what instant are we actually looking at the input voltage? I can't hear you. Yeah, so what is a precise instant of sampling? It is the falling edge of phi of t, right. So, this is the sampling. All right. Of course, life is not as simple as this. In reality, there is a whole bunch of non-idealities. The first one being that no switch is ideal, and it turns out that every switch will have associated with it a resistance. All right. And so, therefore, the bottom line is that well, the output will track the input, but there will be a small delay corresponding to the RC time constant, right. But more importantly, the resistance also adds, the resistor is also associated with a noise source, correct. So, during the tracking phase, how does the circuit look like? Well, there is the input, all right. And so, what comment can you make about the voltage across C? I mean, and by the way, the RC time constant, what comment can we make about the RC time constant in relationship with Ts? Pardon? I mean, that RC time constant must be extremely small compared to half Ts, because you want the input to track, I mean, the voltage across the capacitor to track the input as closely as possible. So, RC is much smaller than Ts, all right. And so, therefore, during the tracking phase, what comment can you make about the total voltage across C? It will of course consist of V in, right, okay. And remember, at the sampling instant, namely the falling edge of the this waveform phi of t, you not only have the input, plus you have a component due to the thermal noise of the switch, right. And what will be the so what comment can you make about the signal is basically V in, whatever it is, okay. What about the noise? Yes, what comment can we make about the noise? It is 0 mean, that is correct. What else? It's a random waveform, that's correct, okay. It's got 0 mean and it's got some mean square value, and what is the mean square value? Kt by c, right. Alright, please understand that when we say the mean square noise is Kt by c, it does not mean that you add square root of Kt by c to the output, right. It just means that if you build a million such circuits, or if you look at the noise associated with the voltage across the capacitance 1000 or a million times, right, you will find that the mean square value of that noise is Kt by c. It does not mean that at every instant of time, every time you measure it, it is square root Kt over c. Is this clear? Right. So what comment can you make about, and so this is what the voltage across the capacitor would be during the track phase, right. And then the hold phase comes. When the hold phase comes, what happens? The switch is opened suddenly, right. So whatever voltage is there on the capacitor, that voltage is, that charge is trapped, right, it has got nowhere to go. So what you are actually sampling is V in plus the sample voltage across the capacitor is nothing but V in plus some noise voltage, where the mean square value of that noise voltage is simply Kt over. Alright. For example, let us assume that the RMS value of the input signal that needs to be digitized is 1 volt, alright, and C is 10 picofarad. Alright. So what comment can we make about square root of Kt over c? Please somebody do the math and tell me. $20? Okay. All right. So all right. So okay. Now if C was, instead of being 10 picofarad, was 100 femtofarads, what will happen to this value? This is how much times, how many times smaller? Times square root of, this is 10 power minus 13, and that is 10 power minus 11. So that is basically a factor of 10 worse. That is now it is 200 microvolts. Okay. So what comment can you make about this in the last instance? What comment can you make about the signal to noise ratio, which is simply the ratio of the mean square value of the signal to the mean square value of the noise, which is and is often expressed in dB, because this is power, it is 10 log, which is 20 log to the base 10, 1 volt divided by 200 microvolts, and that is how much? Is 74 dB. All right. Okay. And so, in other words, this is only a factor of less than, it is about between 3000 and 4000, right. So, 74 dB is between 3060 dB, I mean 1060 dB, 10,000 is 80 dB, 70 is somewhere between 60 and 80, and therefore, it is somewhere between this geometric mean of 1000 and 10,000, which is roughly around 3500 or so. So, basically you say, I mean the practical importance of this is that if you use a small capacitor to sample, all right, you will be stuck with a noise voltage on the capacitor, right, which is large. Okay. In this case, for instance, you already made an error of the order of 1 part in 4000, right. So, if the resolution of your A to D converter that you are trying to realize is much higher, then this is a very bad choice of capacitor to use, right. So, if you are trying to resolve a voltage to better than say 1 part in a million, right, 1 part in a million is 120 dB, right. Okay. And if you do that, then this is grossly inadequate, because the moment you sample the signal, already you committed a crime, right, which you cannot recover from, all right, because you are adding some random thermal noise, I mean some random voltage in addition to the voltage you wanted to sample, that is what do you call dependent on that capacitor value. Is this clear? So, what is the moral of the story? If you want to resolve, or if you want to build a sampler, or consequently an analog to digital converter with higher and higher resolution, right, based on sampling the voltage on a switch using a on a capacitor using a switch, then you see that the value of that sampling capacitor better be sufficiently large, so that the error you make when you sample the input voltage onto that capacitor is way smaller than what you are trying to resolve, right. Okay. So,